Dear students, in this video we are going to study about the AC generator, the principle and working of this AC generator. What are the advantages of a stationary armature rotating field alternator, a single phase AC generator, then polyphase AC generator and three phase AC generator. What are the advantages of three phase alternator? Now let us study about AC generator. First one is the introduction about AC generator. What is an AC generator? This AC generator is a device which converts energy, there is one form of energy into another form of energy, that is mechanical energy into electrical energy. Therefore, it is an energy conversion device as it converts mechanical energy which is used to rotate the coil or the field magnet into electrical energy. Therefore, an alternator produces a large-scale electrical power for use in homes and industries. Here, an alternator, it is generally known as AC generator. So this AC generator and its components are as shown in this figure. This is a stator, rotor, alternator, brace box, slip rings. Now let us see what is the principle behind the working of an AC generator. So here alternators work on the principle of electromagnetic induction. The relative motion between a conductor and a magnetic field changes the magnetic flux linked with the conductor, which in turn induces an EMF. So the magnitude of induced EMF is given by Faraday's law of electromagnetic induction, and its direction is given by Fleming's right-hand rule. Now let us see about the construction of an AC generator. An alternator consists of two major parts. One is stator and the other one is called a rotor. As the name suggests, the stator is stationary while a rotor rotates inside the stator. So here is the stator in which a rotor will rotate. This is a stator and rotor. This will actually rotate inside the stator. In any standard construction of commercial alternators, the armature winding is mounted on the stator and the field magnet on the rotor. The stator, the stationary part which has an armature windings mounted in it, is called a stator, and it has two components, namely stator core and armature winding. The stator core or armature core is made up of iron or steel alloy, and it's a hollow cylinder and is laminated to minimize eddy current loss, which we have studied earlier. The slots are cut on the inner surface of the core to accommodate armature windings. Armature winding, what is that? That is the coil wound on slots provided in the armature core, as shown in this figure. So this is the armature slot and armature core, all these things here shown in this figure. So next one is the rotor. A rotor contains magnetic field windings. The magnetic poles are magnetized by DC source. The ends of field windings are connected to a pair of slip rings which are attached to a common shaft about which a rotor rotates. The slip rings rotate along with rotor, and to maintain connection between the DC source and field windings, there are two brushes which are used which continuously slide over the slip rings. The two-pole rotor is as shown in this figure 4.27. There will be two poles. So we will now discuss the construction and working of two examples, namely the single phase and three phase AC generators, in the following sections. Now let us see what are the advantages of using a stationary armature rotating field alternator. An alternator is generally a high current and high voltage machine. The stationary armature rotating field construction has many advantages. Now let us see one by one. First case, the current is drawn directly from fixed terminals on the stator without the use of brush contacts. Then The insulation of stationary armature winding is easier. The number of sliding contacts, which are called as clip rings, is reduced. Moreover, the sliding contacts are used for low voltage DC source. Then armature windings can be constructed more rigidly to prevent deformation due to any mechanical stress. Next, we will study about the single-phase AC generator. In a single-phase AC generator, the armature conductors are connected in series so as to form a single circuit which generates a single-phase alternating EMF, and hence it is called a single-phase alternator. In the simplified version of AC generator, a singleton rectangular loop PQRS is mounted on the stator. The field windings is fixed inside the stator, and it can be rotated about an axis perpendicular to the plane of the paper. Then the loop PQRS is stationary and is also perpendicular to the plane of the paper. When field windings are excited, magnetic field is produced around it. Let the field magnet be rotated in clockwise direction by some external means, as shown in figure 2.8. Now let us assume that the initial position of the field magnet is horizontal. At that instant, the direction of magnetic field is perpendicular to the plane of the loop PQRS. The induced EMF is 0, and this is represented by origin O in the graph drawn between induced EMF and the time angle, and that is shown in figure 2.29. 4.29, this one. And when the field magnet rotates through 90 degrees, the magnetic field becomes parallel to PQRS. The induced EMF across PQ and RS would become maximum. Since they are connected in series, the EMFs are added up, and the direction of total induced EMF is given by Fleming's right-hand rule. We should take care while applying this rule. The term indicates the direction of the motion of the conductor with respect to the field, and for clockwise rotating poles, the conductor appears to be rotating anti-clockwise. Hence, the term should point to the left, and the direction of the induced EMF is at right angles to the plane of the paper. And for PQ, it is inwards, and for RS, it is outwards. Therefore, the current flows along PQRS. The point A in the graph represents its maximum EMF. And for the rotation of 180 degrees from the initial position, the field is again perpendicular to PQRS, and the induced EMF becomes 0. And this is represented by the point B. So here, this point A is for an angle of 90 degrees and B is for an angle of 180 degrees. The field magnet becomes again parallel to PQRS for 270 degrees rotation. The induced EMF is maximum, but the direction is reversed. Thus, the current flows along SRQP, that is represented by the point C. On completion of 360 degrees, the induced EMF becomes 0 and is represented by the point D. And from the graph, it is clear that the EMF induced in PQRS is alternating in nature. Therefore, when the field magnet completes one rotation, induced EMF in PQRS finishes one cycle. So this is one complete cycle of the plane of the coil with respect to time. So here in this case, omega t equal to 0 and omega t equal to pi by 2. Here omega t equal to pi. Here it is 3 by 2 pi. And here it is 2 pi. So for these different positions of plane of the coil, the alternating EMF will be like this for various angles. So here is 0, here 90, here 180, here 270, and this point, at this point it is about 360 degrees. So this is how the induced EMF varies with respect to time. Next we will study about the polyphase AC generator. Some AC generators may have more than one coil in the armature core, and each coil produces an alternating EMF. In these generators, more than one EMF is produced. Therefore, they are called as polyphase generators. If there are two alternating EMFs produced in a generator, then it is called two-phase generator. And in some AC generators, there are three separate coils. which should give three separate EMFs. Hence, they are called three-phase AC generators. Now, let us see about this three-phase AC generator. So, in the case of a simplified construction of three-phase AC generator, the armature core has 6 slots as shown in this figure. So, slot 1, 2, 3, 4, 5, and 6 slots, which are cut on its inner rim like this. And 6 armature conductors are mounted in these slots. The conductors 1 and 4, they are joined in series to form coil 1. Conductors 3 and 6, they are joined together to form coil 2, while the conductors 5 and 2, they are joined to form coil 3. So these coils are rectangular in shape and they are separated by an angle of 120 degrees from one another, as shown in this diagram. And the initial position of the field magnet is horizontal and field direction is perpendicular to the plane of the coil 1. As it is seen in single-phase AC generator, when field magnet is rotated from that position in clockwise direction, alternating EMF E1 in the first coil begins a cycle from the origin O, and this is shown in 4.31 here. So for the EMF E1, this will be the graph for the first coil. The corresponding cycle for alternating EMF E2 in the second coil starts at point A after the field magnet has rotated through 120 degrees. Therefore, the phase difference between the EMF E1 and E2 is about 120 degrees. Similarly, the EMF E3 in the third coil would begin its cycle at a point B after 240-degree rotation of field magnet from its initial position. So thus, these EMFs produced in the three-phase AC generator have 120 degrees phase difference between one another, as shown in this graph. Now let us see what are the advantages of three-phase alternator. This three-phase system has many advantages over single-phase system, and they are given here. First one, for a given dimension of the generator, the three-phase machine produces higher power output than a single-phase machine. So we can get a higher power output in the case of the three-phase AC generator. And for the same capacity, the three-phase alternator is smaller in size. When compared to a single-phase alternator, the three-phase transmission system is cheaper, so you can reduce the cost. A relatively thinner wire is sufficient for transmission of three-phase power.